Hi, this is Dr. Lesher, and this is another video for Chem 103 about significant figures. And really, significant figures are a way we communicate accuracy. So let's imagine two scenarios. The first is that you're measuring something. Happens all the time in chemistry. How do you write it down? And then the second is you're reading someone else's measurement. And I say this is a communication strategy because the way we write down the measurement, it communicates the uncertainty of the measurement. And as you'll learn, there's always uncertainty in any measurement you ever take. So back to the first scenario, what are significant figures in my measurement? And it's pretty straightforward. All the digits that we know with certainty are significant, plus one final digit, which is usually guessed, estimated. It's a little bit uncertain. So it makes a little more sense to look at an example. This is called a triple beam balance, and you may not have used one before, but the way it works is that you move these sliders around until the pans in the balance are level with each other. And the sum of the weights on these three beams are the sum of whatever it is you're measuring. So here we have something that weighs 300 plus 70 plus 3 point something grams. Now we want to look at this last little slider, the one that's between the 3 and the 4, really carefully. So let's zoom in on it a little bit. It's a little bit pixelated, sorry about that. We can tell that the slider is just past the third little hash mark here, and these little hash marks represent tenths of grams. So we know that it's definitely 373.3, but we're going to take it a step further to get that last uncertain digit. And I don't know it for sure, but I'm going to guess it's maybe 373.35, 0.33, somewhere in there. So yeah, I can't be sure if it's 0.31, 0.34, it's somewhere in there. But we do know it's a little bit greater than 373.3, so we don't want to just leave it as 373.3 grams. So just use your best vision to estimate that last place. And yes, this measurement should have 5 significant figures. So bottom line, when you're recording your own measurements, record all the certain digits and then estimate a last digit. And this is limited by your measuring device. So another example here, let's look at a simulated picture of a graduated cylinder measuring volume. If we use the one on the left, what do you think you can call that volume? I would call that, it's more than 14.5. I would probably call that 14.6, but could it be 14.7? Yeah, I think it could be, just looking at the one on the left. So that last digit, the tenths place in this example, is uncertain. If we have a better graduated cylinder with more markings, then I can see here that it's in between the 0.6 and the 0.7. So I might guess that's 14.63, something like that. But yeah, in that case, the fourth place would be significant. So now on to the, I would say, more difficult job, interpreting someone else's data. So there's kind of 3 rules that you want to remember. First is that non-zero digits are always significant. Second is that if you've got zeros in between other numbers, other significant digits, they're significant. And then lastly, a final zero or trailing zeros in the decimal portion of the number are significant. So I'll give examples of all 3 of these rules. First rule, non-zero digits. This one's pretty much a no-brainer. If there's a number there, it's significant, a number that's not a zero. So, the fact that it's there reflects that the measurement was taken, and so basically the number of significant figures in these measurements here are just the number of digits in the measurement. So here we'd have 4 significant figures, here we'd have, 6 significant figures, and here we'd have 5. Rule number 2 is when we have a zero in between other non-zero numbers. This one's pretty intuitive as well. If you have a number like 406 centimeters, if you measure the 4 and you measure the 6, you kind of had to measure the 0. So in this case as well, basically as many places as you have in the number, that's how many significant figures you have. So pause the video and guess how many you have in each of these. We should have 4, we should have 6, and we should have 5. Rule number 3 is the most challenging one. Zeros are where things get a little confusing. The only time they're significant is when they're after the decimal place and after any other numbers. So what does that look like? They have to be to the right of the decimal point, and they have to be following other significant figures. So this particular mass here would have 6 significant figures. Here, this last 0 again is significant. It's just like these other ones. So here we'd have 8 significant figures. And it doesn't matter whether it's scientific notation or decimal notation. This 0 would also count as a significant figure, so this would be 3. And then in this one, despite the fact that there's these, times 10 to the 12th over here, the significant figures are the 4 that are shown in the scientific notation. Why? Because by writing them, we're showing the world that we actually measured them, and they just happen to be 0. So let's talk about zeros that are not significant. The first is a placeholding 0, and it's a placeholding 0 on numbers less than 1. So these are zeros that are after the decimal place, but the decimal point, but before these non-zero numbers. So none of these zeros are significant. They're only there to kind of show how big the number is in terms of its magnitude. So yeah, this first example, we'd have 3 significant figures. In the second one, we'd have 4 significant figures. One important thing to note is that if you convert this number into scientific notation and express it in scientific notation, those placeholders disappear. So that's kind of one trick you can do to figure out how many significant figures there are, is to rewrite it in scientific notation. And then we've got, a little more obviously, 3 and 4 significant figures. This one, the second type of insignificant 0, is kind of what I call the aesthetic 0. It's in a number like 0.98, when we've got a number less than 1, just this very first 0 is not significant. So this would have 2 significant figures. Really, it's only there to show that the decimal point is a decimal point and not like a little mark on your paper or on your screen. And then the third type of 0 is also a placeholder 0. And so, but this is when we're in whole number category. So when I write just 200 meters, if I don't do anything else, I can't, the way we communicate these measurements is that if I don't indicate otherwise, these zeros here are not carefully measured, and so they're insignificant. 25,000 as written in this way, has just 2 significant figures. So this brings up the point, well, what if I did measure those zeros and I know that they are exact? There's a couple ways that you can do it. Best course of action, in my opinion, is to just express them in scientific notation. So geologists will often talk about the age of the Earth, and it's 4.5 billion years. The 4 is measured, the 5 is measured. The 0 is actually well understood. So the best way to write the age of the Earth is 4.50 times 10 to the 9th. Because if we just write 4,500,000,000,000, then we can't tell that third place, that first 0, is significant. If it's a whole number, then you can put a decimal place at the end. So beakers are relatively inaccurate ways of measuring volumes, but you can usually get it to maybe the nearest 1 mil. So I could say 20 mils with a decimal point after the 0. But right, like with the age of the Earth, sometimes scientific notation is really the only option. The Ice Age started about 10,000 years ago. The first 0 is well constrained, is well known. The last 3 zeros are not exact. So the best way to write it is 1.0 times 10 to the 4th.